So there are 3 parameters for a small signal, as in the case of bipolar we will be interested in. One is of course GM, the other is the output resistance, and the third I made mistake, I should not say capacitance. The model where we are really looking for there is the bandwidth, okay, and bandwidth is related to capacitance. So we will be interested to know in the small signal model of a MOSFET how much is this capacitance and how much are the resistances around, so that we can put a good equivalent circuit, and from that we will be able to get the gain GM, therefore GM and R0, that is the gain part we can get, and also from GM and capacitance we will be able to get the bandwidths. So once we get the equivalent circuit correctly, we will be able to get all the physical parameters known, then circuit parameters can always be evaluated. And if circuit parameters are evaluated, the actual system performance gain and bandwidth, they also can be always found out. So that is the general technique which we will follow. So there is nothing much to say on that. So the first major small signal parameter which makes MOSFET interesting, of course all device has a major interest in the word transconductance, which is essentially in the case of MOSFET is change in drain current with change in gate bias, okay. Now in this case, unless said otherwise, source is always grounded, okay, source is always grounded. So VGS is essentially VG, but if not we will say what is Vs, and then you must find VGS accordingly. Is that point clear? If S is 0 grounded, then Vs is 0, but in case there is a Vs, then you will have to find Vg minus Vs as VGS. Is that clear? So right now I am assuming source is grounded, so difference is VGS. So change in drain current to the change in gate source voltage will give you the transconductance. This is the output and this is the input of a MOS transistor, and therefore this is transconductance. Normally, as I say, we will never operate the transistor in which mode I said, of course cutoff will never, because then the device is off anyway, but in even in linear, because there the gains are very low, so we will not operate, but just for the heck of it I can calculate GM linear as well as GM saturation. All that I have to do is write the current equation and differentiate with delta by delta VGS of that and evaluate whatever is the GM for linear. So if I do this evaluation and I neglect VDS square, because we say VGS minus VT is much larger than VDS, that is why it is in linear zone. Using this condition I can evaluate GM linear is mu Cox W by L into VDS, okay. But that, as I say, is like a resistance. Do you get a point? It is like a resistance. Linear means IDS VDS characteristic is proportional, it is a resistance. So this is essentially evaluation of a resistance. However, we are not very, and is also short formed as beta. Okay, my symbols and book symbols are different. Please note down somewhere. I have been habituated 20 or 30 years. K, what is constant we use in all books, Kn or Kp, I write beta n and beta p. Is that correct? Kn dash is Bn dash, Kp dash is Bp dash. Beta n we define as beta n dash into W size, W by L. That is to just smaller the expressions, because if writing every time mu Cox W by L, we just write betas. Beta has a what units you can think? Can you suggest from here what will be the unit of beta? If you cannot get, you find from here. This has a unit of volt square, current has a unit of amps. So amps per volt square is the unit of beta or K, whatever is the book. Why I am saying K? Because I just today, after many days, I saw the book which I constantly say read, Cedar Smith book, and they have used K as the constant, okay. Why they have used it, maybe I just want to know how to operate SPICE. SPICE stands for what? S of course is simulation, okay. P must be program, okay. Simulating program for special emphasis on integrated circuits. This is a Berkeley program which solves circuit, simple network, nothing great, nothing simple or nothing great, just solve nodal equations IGV and nothing more. All that will happen, it will have a matrice because I will be I1, I2, I3, V will be V1, V2, V3s, and therefore G will be, and G will also have the similar matrix value. So you will have a some kind of a matrix solver. So all that SPICE does it, but SPICE require models for the transistors. So it requires constant W by L, COX, TOX, VT, everything it has to be specified. There is a default parameter for a given technology. Let us say 5 micron process, they will give these values, it is called default. So initially when we are not giving our data, we can assume whatever SPICE parameters are there and just solve the circuit for given input output circuit parameters. Is that correct? So SPICE has an advantage, it can solve digital, it can solve AC, it can solve mixed signal, it can do all kinds of analysis very easily. Okay, and it is relatively faster, it's come from Berkeley and it's an industry standard. Of course SPICE has many versions, model versions, like the one which we are using for say 90 nanometer now has a, it's called BSIM models, okay, that is the Berkeley simulating models, which is level 3, and the model we are using is 58 or 61, something recently, I don't know, maybe 58 was the last. So these models keep changing as the device physics start changing because of shrinking. Otherwise basic idea in SPICE remains same, it solves circuit or it solves a network. Okay. So I think you should know this because some problems we may give you which need not be analytically solved, it may be a little complicated circuit, but then you can substitute there and by stroke of luck everything will come correct. Now that is good thing about simulations, it always gives you result, okay, irrespective whether you are good student or a bad student. Okay. Now I do not mean bad in any sense, but I mean those who are not wanting to do, even if they substitute some number, some result will come. The only problem with SPICE is, and which any simulation program is, how do you know the result you got is correct? Because you gave something and got something. Anyone can do it, even a kid of 3 years can clean something and make something, it does not mean he is correct. Okay. SPICE is correct because it will receive something and it will get you something. Whether device in saturation, not, it does not know anything, it only receives values, okay. It is a mathematical tool. There is where your intervention is required, that you should know what you are feeding, and that is why that much part you should know better. Is that clear? Otherwise SPICE does almost everything in the world. Okay. All industries have, all designs of analog digital mixed signal circuits, RF circuits are using SPICE. SPICE are different model, RF model, this model, various models. By the way, the versions which we use called Spectre or very different companies, each is a very costly business. Typically one computer license SPICE version may cost you $1 million. Of course this is called industry standard, but the academic standards are much lower and we may get it in 5,000 rupees also. Okay. So that is why accuracy is what we get and what they get. Okay. So do not worry, if you do not know, I think if you sit on a PC lab someday and some basic introduction someone give you, you will be much more, I think I use much less SPICE now compared to what I used 15 years ago, 20 years ago, than what you can use, and it does not require great, it can be even downloaded on your own PC laptop if you have, and it does not require huge memory. The SPICE version which I am talking, which is the old version for a 5 micron process, that is very cheap 3G version, and you can always try circuits on that. The results cannot be as accurate as could have been on the cadence tools, but it is good enough for our course. Is that okay? So please learn SPICE because it has nothing to do with my course. SPICE is some kind of a general tool required for digital, analog, any circuit you do want, even communication circuit. At the end, even in communication you will get some circuit, okay. Solving a circuit is easiest on SPICE, okay. There is another program which does very great job, is MATLAB. I do not know whether you already started working somewhere, because signal processing people cannot survive probably without the MATLAB or vice versa, okay. Okay, MATLAB would not have been, of course MATLAB also has a circuit simulator, okay, but it is not as good as SPICE, so better use others. Okay, this is all general because as second yearites you should now start thinking ahead, and I am trying to push you to little ahead of what you should be, as you are. Okay, The interest for us is in the in analog circuit we said MOS transistors are always maintained in saturation. What does the condition in DC way we say when device is in saturation? What is the condition of VGS VDS? That VGS minus VT should be smaller than VDS at any point, okay. Every time VDS should exceed VGS minus VT, okay. If that is so, one can say the current equation then can be written as beta by 2 VGS minus VT square 1 plus lambda VDS. This is current when the device is in saturation. If I take delta of delta VGS of this, now under this case, slightly interesting case we should look for, our assumption is VT is constant, okay, VT does not change with VGS, does not change with VDS. This is slightly secondary, we shall assume is okay, does not matter, okay. In real life VT is not a constant quantity. So when I differentiate that VGS also, VT also has to be differentiated, then it becomes more complicated expressions and hand solving becomes sometimes difficult, and SPICE does this automatically, you do not have to think, okay. The best thing about SPICE is it does not allow you to think, and that is good for us, okay. So if I initially for MOS circuit unless stated otherwise, we will assume lambda to be 0, only what cases we will assume lambda to be 0? When I write currents. But when I write R0, I will not make lambda 0. What does that mean will be? R0 is how much? Infinite. Is that correct? Lambda 0 slope is 0, which means resistance is infinite. But that is never infinite, and therefore calculation of R0 will definitely you get a value of lambda. Otherwise in normal current equation, if you neglect lambda, nothing much worse will happen in actual analysis, okay. So initially to get to a correct simple values, I neglect lambda, so 1 plus lambda VDS is 1, and if I differentiate this with VGS, then it becomes GM, so not beta dash, sorry, maybe, or if it is a beta dash, I will just for the sake of correctness, I will multiply it by W by L, but that dash unnecessarily came there, but does not matter. If I substitute the current equation assuming lambda 0 back to this expression, you can write beta by 2, okay, beta VGS minus VT, I can write beta by 2 VGS minus VT square into 2 upon VGS minus VT, then the first part is IDS, is that okay? This part is IDS, okay. Okay, also in book this S part is normally not used, they only use ID. Please, I write IDS because from the device side current cannot be drain current unless it reaches source, okay. So in our case we always believe that it should be written IDS. If you write ID, it's okay, they are saying drain current, which drain current has to go to source anyway, okay, source is grounded. But said and done, my symbols are more from the device point of view because we have been working on devices for 30 years, so on design, so on circuits, so our symbolization is more from the device side. So I can write 2 IDS upon VGS minus VT, but what is VGS minus VT we said? It is called over voltage VOV, so it is 2 IDS by VOV, so GM is 2 IDS by VOV. If I instead of doing this, I replace VGS minus VT from this in terms of GM and beta, I repeat, I replace this VGS minus VT from this expression, that is 2 GM upon beta under root of that as VGS minus VT, and substitute back, I can rewrite GM as 2 beta N IDS. Is that clear what I wrote? This is IDS, is that correct? So 2 IDS upon beta n, under root of that is VGS minus VT, substitute here that value and you will get GM is equal to 2. This expression many times we use, 2 beta n IDS. So if I am given a bias current, I am given the sizes, given the technology that is beta n dash, mu C ox, so I can immediately evaluate what is the GM of the transistor I am going to use. Is that clear? This is assumption is that someone is giving me VOV, but if I am given IDS only, still I can evaluate, Is that clear? So that is the method of evaluation. Either cases can be used, okay, either cases. They are same, by the way, expressions are same. The second parameter of interest to us is R0, which is the output resistance, and I said you other day it is 1 upon lambda IDS. It is also written as VA upon IDS, VA is hourly voltage. Also can be, we also explained other day that lambda has some technology parameter called lambda dash, and that is why what I said is that day that lambda is lambda dash, which is technology parameter which is fixed to us for a given technology, and L is the channel length. Why I wrote this? Why I wrote this expression in specific? Can you think R0 will lambda dash for a given technology is fixed, okay. IDS is my bias parameter. I am going to decide 1 milliamp, half a milliamp, whatever way I want, 2 milliamp or 1.5 milliamp. So if I want to increase R0, what should I increase? Channel length. For the circuit person, this is foolish because I am getting a transistor already given on board. I cannot change length. But why I showed you this? Because tomorrow if you become an analog designer, that is chip designers, that time what parameter you will start controlling for R0? The lengths. I will start increasing lengths. But if I increase length, what I will lose there from here? GM. Is that point clear to you? The other day, that is why I brought this expression. If I increase channel length, I will improve R0, which is obvious, okay. Is that clear? However, if I increase channel length, W by L will go down and therefore GM will go down. Is that correct? So now you have to understand in design, why it is called design? Because if I control R0, I lose track on GM. If I start controlling GM, I start losing track on R0, and that is what people say, I want gain of this much. Now the designer has to be, I want so much GM and so much R0, how will I get? That is where the whole design issues are issued. In this course, R0 is fixed, GM is known, but I am just trying to give you that what is the design word coming from, okay. Analysis is shown, from there we start thinking what spec I have to meet when I am designing, okay. Is that okay? Yes. Who said? Oh, you mean current gain? Yes. That is because MOS transistor is not a current driven device. So obviously IGs are treated 0 in fact. So you can say infinite, okay, IDS by IG. No, in the sense, but transconductance is with reference to voltage, input voltage, not from current. We are across even an insulator which is a capacitor, voltage can be created. So I am saying change in input signal which is voltage, I will still see the output current varying, and therefore that is what I am interested in. What is the change in output current with reference to change in input voltage? Is that correct? Current gain is yes, it does not exist in the case of MOS transistors, because IG, as it says, there is no DC gate current, at least unless we say leakages exist in the case of. By the way, that IG is not 0 now, that is our worry. But today in course, yes, IG is 0. That means insulator is perfect insulator, no DC current can flow from gate to the any of the substrate source or drain. That is why the insulator was kept, okay. However, in real life, as I say, that issue is now worrying us, okay, but not for this course. Okay. Very good, thinking is very good. So if I compare the two before we go to circuits, I wrote an expression GM is equal to 2 IDS by VOV. Is that clear? GM is equal to 2 IDS by VOV. If I use this expression, I get GM by IDS is 2 by VOV. Is that okay? Simple. Typically, VGS minus VT should not be very large. Why it should not be very large? Because device has to remain in saturation, and condition there is VDS should be larger than VGS minus VT. So VGS minus VT, if it is too large, then device may not remain in saturation. But if it is too small, the current made available to you, because current is proportional to VGS minus VT square. So if I reduce too much VGS minus VT, I don't get current at all, okay. So I must balance, I must have VOV which is relatively higher but much smaller than possible VDS values which I am going to use. Is that okay? VDS has to be larger than VGS minus VT or VOV as we call it. If we reduce VOV too much, then the current made available is very small, okay. However, since I want to push large current for deliver, I cannot reduce VOV too small, but I do not want VOV to be very large because then my condition of saturation may not be valid, and therefore I keep somewhere around 200-300 millivolts, some kind of values which most technologies use. It can be at best 500-600 millivolts at best. Okay, is that point clear to you everyone? That how, why we, this value typically 200 millivolt can be 500 also, just to give some criteria. If I put this 200 millivolt value, I get GM by IDS roughly equal to 10, okay, GM by IDS is equal to 10. Now if I use the similar value, please take it, if I increase VOV, then GM by IDS will be less than 10, is that correct? GM by IDS will be even less than 10. If I look at BJT, what is the value there we calculated for GM by IC? QI by Q by KT. What is GM? QIC by KT. So GM by IC is Q by KT. Typical value at 300 degree Kelvin is how much we calculated? 38, okay. So we see this number is 38, and how much is GM by IDS is going to be? Less than 10, even less than 10, 5, 4, it can be of that kind. So do you always feel that GM by IC will always be larger, at least 3-4 times larger than 8 times larger than GM by IDS? What does that have influence at the end of the day? Therefore, as far as this part is concerned, providing GM by IC ratio, GM by I ratio, bipolars are always superior to MOS transistors. Is that clear? Bipolars are always superior to MOS transistors. So is that point clear? When I day one I said bipolar circuits are far superior compared to MOS circuits. But then why are we working on MOS? Because world has forced us. They say digital circuits are going to be only on the MOS, because MOS performance on digital is far superior to BJT, much smaller circuit, much low power circuit. So if I had to do digital and very small technologies which has a very small voltages, then I will work only for MOSFETs. But I do not have only analog blocks to be sold, I have to be part of this digital block. So I say, okay Baba, I will work on MOS, okay. So that day one I said, why analog people are facing problem? Because they have been given bad tools and say produce the best designs. How can I do it Baba? Everything is stacked against me, and he said no, do better. That's exactly what we do for you. Lot of courses we give you, lot of home assignment, lot of this, and expect you to get A grade in every one of them. That's what the life is all about, okay. So please realize that this is nothing to do with my course, it's true for our life. So we are just following that, okay. Okay, let's look for limitations as we did for bipolar. What is the bipolar limitation? I say how much signal should be? Less than kT by Q, sufficiently smaller than kT by Q. Let's see what happens in the case of MOSFET. This is a typical amplifier shown here, but we will not look for amplification here. We are just trying to say there is a power supply, there is a ground, drain source, there is a RD, and we say there is a capital VGS is the DC bias, okay, over which a AC signal of small VGS is overriding. What is it called in maths? Superposition. So a DC signal is superimposed by an AC signal, and we expect the output voltage also will have then two parts, DC part and AC part. And if I want to get rid of DC, what should I do? Put a capacitor, then only AC will pass. That is what amplifiers will do later when we only look for small signal AC outputs. So if this is V0 this, and I know IDS, what is this IDS means? This is the total current DC plus AC, which is equal to beta n by 2, and assuming right now which devices? n channel devices will be used till said otherwise. Beta n by 2 VGS minus VT plus VGS, you are superimposing square 1 plus lambda VGS. As usual, lambda is small, the second order term is neglected, and therefore, so what is the small current, AC current then will be IDS will be how much? The net current minus the DC current. ID capital DS minus capital IDS, then that is the AC current. Is that okay? What is AC current? Total current minus the DC current. So I just subtracted. So I now use expression for this, this is the expression for total current, this is the expression for DC current. Is that okay? This is the total current, this is the DC current. So I just subtracted, nothing very serious I did, and I expanded the terms to see which terms cancels. So if I do this, if you write down, okay, is that point clear? I just want to know how much is the AC current I am getting, okay, or small signal current I am getting. 2 beta n by 2 VGS minus VT into small VGS into 1 plus VGS upon 2 capital VGS minus VT. This is just subtraction, nothing very great about it. Okay. Which terms will cancel? VGS capital VGS minus VT square term will cancel because that DC and this DC will move away. This is the term remainder which can be rewritten in this form. Is that okay? Last expression is okay, just collecting the terms. Okay. Okay. Is that expression wrote down? Okay. So just subtract, in case you are not written, just few, again I have written, if those who are not written can write. So small IDS is GM times VGS into 1, then I replaced my GM formula in the first part of the expression, and therefore I get IDS is GM VGS 1 plus VGS upon 2 VGS minus VT. Now if I want to say this term I do not want, which one? 1 plus term I do not want. Then what is the condition I am saying? I want 2 VGS minus VT should be much larger than VGS. Numerator should be smaller than denominator by order. Okay. And if this condition I force, then I get IDS is equal to GM times VGS. That is what small signal equivalent model I want. If I have a small signal input voltage VGS, the output AC current should be GM times that VGS, as straight as that. Is that clear? That is what the network theory is saying. I is equal to G times V. So I want that expression to appear. This can appear only when it can appear? When 2 VGS minus VT is larger than AC signal, which is VGS. If you put some typical value, say VGS will be order of say 2 volt, VGS minus VT will be order of say 2 volt, then VGS should be at least much smaller than 2 volt, and this is slightly better than bipolar degradated, there it is only 26 millivolt. So MOS has little advantage that the AC signal can be slightly larger than bipolar. Is that point clear to you? Why I brought this expression to you, that compared to bipolar, MOS transistors, small signals can be little larger, okay. But what is the problem there? GM is smaller, as we see earlier. So all that we say, if VGS can be larger, but GM is smaller, so GM VGS is not increasing even as compared to bipolars. Is that clear to you? So all said and advantages, एक तरफ बोलना बाद में oh nothing ऐसा. Small VGS typically less than 20 millivolts. See order means this will be VOV, so 200 millivolts order, so 10 times करो उसका. So roughly 10 means 1 order. Okay, so 1 order less होना चाहिए expansion को 0 करने के लिए. So typically 20 millivolt, but in there we don't even use 20 millivolt, 5 millivolt, 3 millivolt, at best 10 millivolts in bipolars. Here we can exceed little, but I tell you what is the problem, this GM is much lower, so GM VGS will not be larger than bipolar either way, okay. So that is where the issues are, that why bipolar and why MOS, okay. Yes, I agree with you, but what did I do is, I have substituted linear part, voltage part there, I have never said the current is linear, but I really want GM to be linear, okay. So I said, okay, this is a non-linear term, definitely it's a non-linear term. I am subtracting also another non-linear term out of it. So this term is non-linear. To make a linear case, I said this term should be smaller. What you are saying is true, this expression is non-linear. So to make it linear, I said the condition I can have is 2 VGS minus VT should be an order higher than the small VGS, and then I say it's linearized. Because all the time I say these circuits are called linear circuits, so I want to linearize it faster, okay. So I say what condition I can linearize, so I say okay, if I use this I am linearizing, is that okay? Okay, so equivalent circuit of a MOS transistor at the end of the day, using so called what we did, you have a gate, you have a drain and you have a common source, okay. There is no current or resistance right now between gate and source, because gate to source resistance is how much? It's an insulator sitting there, so how much? Say hundreds of mega ohms, so practically open circuit, okay. But what can happen there, what can occur instead of resistance? The capacitance. We have not looked into right now capacitance, we only looked into the simple equivalent part coming from I and GM. The output current, just now I wrote GM VGS, so it should be GM VGS, okay. And if I include my R0 term, then the equivalent circuit of a MOS transistor is VGS here, GM VGS shunted by R0, and how much will be R0? Much higher, tens of mega ohm or 1 to tens of mega ohm. So this will be relatively good current source, is that clear? It should be good current source. But just take a case which is interesting case, yeah, or maybe our circuit is here. If I, that circuit figure, if you use this circuit, where this RD will appear? Where this RD will appear in this small signal? RD is between, this has to be understood, all of you know well, but I restate, what is the actual for AC, this point is ground, this point is ground for AC. So RD is between drain and ground. So if is that clear? Drain and ground. So where this will appear here externally? RD. Is that okay? So RD will be shunting R0. R0 is of the order of how much? Tens of mega ohms, at least one, but even 10. Depends on what? Lambda, which will be given to us, say whatever lambda they say. If that is so, what is the actual resistance I am going to get here? RD only, because RD will be in few kilo ohms, tens of kilo ohms, 20 of kilo ohms, but this will be in tens of mega ohms. So essentially what will be V0? If I calculate V0 here, after I have another slide, but just for the heck of it, how much will be V0 minus GM VGS R0 parallel RD, and if RD is much smaller compared to R0, it is GM RD. So is that correct? At the end of the day in a circuit, the load decides the output voltage, is that clear? But in an integrated circuit, there are no RDs we put, okay. I will show you some at the end of the course what ICs do, okay. We will replace RD by a transistor itself, and if that happens, this will be much larger, and if that happens, this will be typically order of R0 itself. So for integrated circuit, gains are GM times R0, but for normal our open circuits with transistor given to us, the gains will be decided by RD, which is provided externally by us. Is that correct? GM times RD is what gain will be actually appear. Is that clear? This part has to be understood because R0 is very high. So GMR0 is okay, that part let me do again before we go here. The expression, if I use the same ones, Vin is equal to VGS, so V0 is GM VGS R0, so GM R0 Vin, so the V0 by Vin is AV is minus GM R0, is that correct? This is called intrinsic gain of an transistor, this is called intrinsic gain of a transistor, is that correct? This is not extrinsic, why it is not called extrinsic? Because RD is not connected, is that correct? This is intrinsic, is that okay? Why is called intrinsic? Because there is no external component right now sitting on it. It is internal to what is this gain. Okay. So this is also to some extent figure of merit for us. What is the maximum gain this transistor can provide? Okay. Typically say, let's say this is 10 mega ohms. GM will be order of some milliamp per volt square per volt. So you can say this will be order of 1000 at best of times. Is that correct? It will be highest value will be 1000. So when I shunt it with RD, whether it will be more than 1000 or less, always be less than 1000, is that correct? So the typical gains you can get is 10 to 100 to 400 or no more than, not even 1000, is that clear? 1000 is what we say is the upper limit, okay. So an analog amplifier cannot actually intrinsically go beyond say few hundreds of an amplification, but actual the amplification will be much smaller as RDs will decide. I will show why RD also decides something. Okay, if GM is 2 IDS by VOE R0 is this, I can say GM R0 is 2 upon lambda VGS minus VT or 2 IDS, something like this. So given a over voltage for a circuit, I can also find the intrinsic gain, is that correct? Given the lambda and VOV for the circuit or transistor, sorry, then I will be able to find what is the intrinsic gain of this transistor. So why I am giving you this? Because when I am making a circuit on a board, how to choose a transistor from the box they give you. So okay, I say I want so much gain, so let us see what is the intrinsic gain I can get. These value will be specified in the manual data sheets. So you find okay, so this is 500 is fine, then that much is good enough for me. This has to be done when I actually go on the board, beforehand I should know how much is this, is that okay? So certain things as a when we do experiment we ought to know a priori, these are the way a priori values are evaluated. Now coming to the last part of the transistor which is related to bandwidth is the capacitance. This is a typical n-channel MOS transistor shown here. This is your source, this is your drain, this is your bulb, this is your gate, separated by oxide of thickness Tox, and the oxide capacitance is always expressed as oxide capacitance per unit. Why did we do this? Because this device people have habit of using charge densities, is that clear? Q, capital Q they will say, charge density. So Q is equal to CV. So if I use charge density and if I don't use C as per unit area, then that equation is not balanced. So I say either be per centimeter, udhar bhi per centimeter square. Q is CV सब जगह. That's why they did it. ऐसा मैं यहाँ बता रहा हूँ, वहाँ कुछ और बताऊँगा. Okay. So Cox is epsilon ox by Tox. For a different technologies, Tox may vary. What is the smallest Tox right now in the new Intel 22 nanometer Intel processor has come? How much is Tox they are using? I already said technology is known by the number I keep telling, 22 nanometers. Okay, 22 nanometers. So something less than that will be, much less than that will be yours. These days we actually want less than some angstrom, say 1 or 2 angstroms of oxide. Okay. Now we cannot create 2 angstroms of oxide. Why? Can you tell me why? Because the bond to bond, atom to atom bond distance itself will be not less than 1.6 angstroms. Okay. So for even one monolayer of atoms, you cannot have that kind of thickness of oxide. Okay, because you need 2 atoms minimum, silicon and oxygen. तो उसका सेपरेशन ही इससे कम नहीं है, उनका डाया भी है, तो ऐसा कुछ कर नहीं सकते. तो what how can we do? We are still working on less than a nanometer kind of oxide thicknesses. How do we do that? Epsilon, we are increasing proportionately epsilon so that T also can be increased, capacitance is held. Okay, that is why it's called high K dielectrics. The new technologies use no silicon dioxide but dielectrics like hafnium oxide, hafnium oxynitrides, gallium oxide, lanthanum oxide, European oxide. For example, I have been working in last summer on very stack of lanthanum and gallium oxides in Japan when I was 2 months there. So we are looking for very high K, typically I am looking for a K of 60 or 70 and we may use it in memory dynamic resonance. Okay. So the kind of research going on in the material side for the circuits is high K now. Okay. So the capacitance is associated, you can see from here, if there is no inversion channel, what is the capacitance between gate and bulk? CGB. Is that correct? If there is no channel, what is the capacitance? CGB, which is nothing but how much? Cox, no inversion channel. Let us say there is a inversion channel throughout. Okay. Then bulk is not connected now. So what is the capacitance now associated? Between channel has heavy number of electrons. They are connected to N and N. So again a capacitance is Cox. Is that correct? Instead of bulk, now the black backplate is provided by the channel. Earlier the backplate was here, there was a resistance here but much smaller and there was a capacitor. Now that R is also removed, only a capacitance. Now the problem with MOS transistor, if he has, Mr. Saha has told you, this is a distributed capacitor. This is not uniform everywhere. So what do we do? Actually there are n such capacitances sitting here. So what we say, for simplicity, half Cox is provided at the source end and half capacitance is provided at the drain end. So I say CGS and CGD will be half Cox and half Cox. Is that correct? Is that point clear? CGS half Cox, CGD half Cox. And if CGD doesn't exist, I will give full Cox to CGS. That's the way modeling is done. Okay, so here is something. CGS is half Cox into gate area. How much is gate area? W into L. CGD is also half Cox into Ag, which is again W by L. But let's take it same as CGS for CGD, which is Cox times W into L. Is that correct? Simple. In case there is no channel, what is the capacitance? Same, Cox into W into L, because there is between the bulk, the gate area and the oxide, nothing else. So CGB is also Cox into W. But when the device really goes into saturation, okay, sorry, this is not correct, this half is only for non-saturation. In real life, it is 2/3 Cox at the source end. Okay. Why it is so? Because if channel pinches earlier, there is no drain end capacitance. Is that correct? So I say all of this Cox is now pushed to source side, and CGD I say doesn't exist as it. Though CGD may come because of the depletion layer at the drain side. So CGD is not zero, but that CGD which was coming from oxide is now pushed to source side. Is that point clear? I repeat, since in a MOS transistor, when the channel pinches here, okay, the drain is now not connected to the oxide because there is a semiconductor depletion layer here. So the capacitance here is due to depletion layer and not due to the oxide. Is that correct? Not due to the oxide. So CGD is now essentially because of the semiconductor capacitance on the lateral side and not so much from the upper side. Whereas if you look at the source side, oxide is still sitting here. So all of Cox is pushed to the source side. Okay. So in saturation, you may use Cin as Cox into W by L in any mode of transfer, any mode. Okay. That may not be accurate, but that is good enough for our calculation as far as numbers are concerned. In physics, yes, we have to find what exact values we get. Is that okay? Then there are two more capacitances we see. What is this N plus P? What is N plus P in physics? Diode. This N plus P is also a diode, reverse bias. Why it is reverse bias? I say if the bulk is grounded, what is the voltage I will apply on drain? Plus value VDS. So this is heavily reverse bias, large depletion layer will come here in fact, okay, and therefore there will be a smaller capacitance on this side, okay. However, even at zero bias, the diode is reverse bias, there will be a smaller depletion layer, but there will be there, and there will be CGS also. And if source gate, now can you think I can actually putting source to ground and still this reverse bias can be increased by what? If I put minus value or rather for P minus voltage at the bulk, source to bulk voltage will increase minus. So is source to drain to bulk also will increase further. Is that correct? So if there is a VSB available per se, then the capacitance will change. Is that okay? Is that okay? The depletion layer will enhance with applied bulk bias. Okay, and if that happens, the capacitance will increase or decrease? Decrease or increase? If I increase VSB negative more, what will decrease? Decrease, because X will increase epsilon by D. So D increases means capacitance falls. If the capacitance is smaller, it is more worrying or it is larger is more worrying? Smaller is worrying me more. Why? 1 upon j omega C will come into picture then, okay, at frequencies of my lower frequency. So I am worried how much this C is, okay. Therefore, I calculate diode capacitances assuming step junctions. What is this phi SB and phi dB I wrote there? Which are these terms? Built-in voltage for source drain junctions and source to bulk and drain to bulk junctions. Generally, they will be same, but not every time. There is a device which is called lightly doped drain. What is the structure called? LED MOS. Okay, drain is lightly doped. थोड़ा एक ऐसा एक और N लगाते हैं. In that case, the dopings are different and phi is also different. So if general formula we write phi SB and phi SB and phi dB, but normally phi SB for equal to phi dB in our case. Okay. So I can calculate all capacitance. In our course we may not calculate, but we just want to show you that we can evaluate for a given technology, given bias, the capacitances. Yes. It depends on whether the device capacitance is in series or capacitance is in parallel. Is that clear? If it is in series, something else will happen because it will path shorting or opening. In shunt, if it is open, good, because it opens, okay. But if it shorts, then I am worried. Is that clear? In series, if it shorts, good. That means that component is not relevant. In shunting, parallel, if it shunts, everything goes down. So capacitance where decides the choice. Is that clear? So I don't a priori want to tell you which will be where. Depends on wherever it occurs, I will see whether the impedance offered for me puts me into difficulty or it doesn't put me in difficulty. Either way. Okay. Okay. So typical equivalent circuit of a MOS transistor for capacitance shows a CGD here, a CGS here, then between bulk and the source and bulk and the drain. Okay, these are the minimum 4 capacitance can occur in the circuits. Is that okay? However, I repeat, these values will be specified to you. Maybe in the first tutorial I may solve 1 or 2 values to show what they get, but otherwise circuit people are not asked to evaluate this. Okay. Why I showed you this? Because you should know connection. You have done a course on devices, from there I am picking those values. Okay. Finally for this, therefore, we have the FT. What is FT value we said other day? Unity gain frequency, which is Gm upon 2 Cn, capacitance at the input, or 2 pi Cn if Ft, and the input capacitance is, can you tell me why I am adding all of it? Sorry. Are you getting both together now? This and this? At this end Cn, please remember unity gain means this is directly connected to the ground, V0 is 0, is that point clear? How do I call Ft? Voltage, output voltage is shorted. Okay. So for this case this is ground, means this is also in parallel to CGS, is that correct? This capacitance and this capacitance both are parallel. And why this CGB I have added? For the sake, in case there is no inversion channel, device in off state, whatever is the capacitance is CGB. Whatever happens, whichever is dominant I will put. So I said okay, in general I should write CGS plus CGD plus CGB. In general CGD plus CGB will be 0 for saturated device unless stated otherwise, then it equal to CGS, which is Cox into W by L. Is that clear? So in devices we do evaluate everything and verify. In circuits we will give you this value and just forget this. Is that okay? If I specify you CGD, you do use that. If I not specify, don't use it. Okay. If I say this is 0.4 femtofarad, yeah, you actually connect. Is that clear? Is that point clear? So any capacitance, if specified, don't ask me physics. You say okay, these are the values. Okay. As far as circuit is concerned, we are only looking which connect where. Okay. But how to get them is physics, which you have learned. I thought you should know connections. Because I promised you that first 2-3 hours lectures I will explain you from devices how do we come to circuits. Okay. Why we don't show so much in digital? Because there 0-1 में कोई फर्क नहीं पड़ता, कुछ भी कुछ करो. I told you just now, CGS is the gate to source capacitance, which is oxide capacitance, half Cox. CGD is half Cox if the channel exists throughout. But in analog circuit, drain will not be getting connected. Okay, drain is saturated there, so no CGD will occur. So all the oxide capacitance is given to CGS. Okay, CGB is the value if there is no channel, gate to bulk capacitance exists. That is the oxide capacitance. If no channel, VGS is very small, less than VT, no channel exists, between gate to bulk there is whole capacitance of the oxide. So W into L into Cox. Now all three may not be exist simultaneously. Is that point clear? But in general all three can be as if added, whichever dominates in zone of operation, use that. In our case I already said CGB and CGD can be neglected as far as Cn is concerned, and you write Cn is just CGS, sorry this is CGS, sorry if I made mistake, CGS which is Cox into W by L. Is that okay? This is to show you in general what specific is what. In saturation the other two can be neglected. Okay, and CGS is given all of it. Okay, all of it. Is that okay? Now you should have asked that sir L correct है क्या, कि source तो channel length तो इतना ही है, but that's assumption. That's why I said 2/3 था ना वो 2/3 को हटा के मैंने पूरा कर दिया. वो 2/3 भी accurate नहीं है, because से trapezoidal rule लिया है, वो trapezoid है नहीं, exponential है. Okay, कहीं के error function है, तो maths बहुत ज़्यादा complicate ना करें, इसलिए हमने कहा अच्छा if I increase little bit more, what is I am doing actually? I am protecting myself. Some other parasitic would have anyway added there per se. So if I use little higher value, my bandwidth may go down. Is that clear? So I am always on the safer side because I am using 10th of that, 100th of that in my use. So if I initially say 100 megahertz and use 1 megahertz, it's okay. It would have been really 120 megahertz. So what? I am actually reducing the operating frequency even lower so that I am guaranteedly remained in this operating values. Is that correct? So by little bit enhancing that, see, I am not actually losing in circuit anything. Is that I am just saving my, what is it called? Engineering approximation. थोड़ा सा आगे रख लेते हैं ना, थोड़ा मार्जिन रख देते हैं. आपने कोई गलती किया, बिल्डिंग गिरना नहीं चाहिए ना, आजकल गिर रहे हैं इसीलिए मार्जिन नहीं रख रहे ना. If there is a cutoff situation, gate voltage is less than Vt, the MOS transistor still has a capacitance between gate and the bulb. That's CGB. Is that correct? That is Cox. Oh, so what you are saying, adding, I don't mean really that all of them should be added simultaneously. For a given mode of operation of a transistor, one of them or two of them will be working. Let us say it is in linear mode, CGB will be 0, each will be half half. Yeah, because, your point. Since the channel exists here, it is screening the bulk. Channel has a large number of electrons, one side is source connected, so plate is already made available to Cox. There is a resistance here which you may say object to. The semiconductor resistance is in series there, but that we are anyway saying is much smaller. Okay, because the area is very large of the wafer, so epsilon rho L by A. Why that resistance is smaller? Rho may not be very small, okay, but A is very large area, so the resistance offered by the substrate is smaller. In a very high frequency, maybe we will have to worry that also, but as of now, if it is in saturation, I said the channel moved away, so I say okay, all capacitance due to oxide I give it to source because drain side I don't. So when I say I am summing 3, I don't mean actual calculate, and for a given mode of operation I will use whichever the value I should get. If off, I will use CGB. If linear, I will use CGS plus CGD, but both I will ascribe half half, so it is against COX. And if it is saturation, I will only use CGS and I still use COX. Is that clear? So I am only saying in general they are together, whichever dominates will take care. Okay, is that okay? Okay. So finally, before we leave this, this is the equivalent circuit of a MOS transistor. ये एक टर्म अभी इसमें से निकालनी है, वो मैं अभी थोड़े देर में बताता हूँ. एक टर्म इसमें एक्स्ट्रा है, उसको भी डिराइव कर देते हैं, बाद में आपको आगे दिखाते हैं. This is called high frequency MOS model. Okay, this is high. Why it is called high frequency? All capacitances have been added. Okay, in small frequency, what will we do? We will remove all capacitances, as if 1 upon j omega c is either open circuit or a short circuit if it's series parallel, whichever way it happens. We remove all of them. Okay, there is a gate here, there is a drain here. Something I have not drawn here also, maybe you can think of it there also. There will be another resistance here which is RGG dash. There will be another resistance here which is RDD. There will be another resistance here, source to source dash, RSS dash. I will just explain you, maybe we may use this, we may not use this as GMB terms. This is not small, huh? That is why I have given you that term. So what is CDB and CSB? These are the diode capacitances. Is that correct? CSB and CDB are diode capacitor, drain to bulk, source to bulk. CGS अभी आपको बोला, CGD अभी आपको बोला, R0 is known. This is gate. There may be a gate resistance itself, RGG dash. There will be a drain resistance also available. There will be a source resistance also. What are these? Because of source and drain n plus regions and contact, they will have some resistance like base collector abhi are shown in bipolars. There will be a resistance RGG dash which is not very relevant. Why? Because no DC current really flows through this. Okay, but for AC there is a drop there. Okay. So one has to worry about that. Okay. Generally it is small because of metal use there. GM VGS is the current source proportional to your VGS. Input is VGS, gate to source. Current source at the output is GM times VGS. This is our RGS. Now the term which I have not yet explained is GMB, not VGS. I am sorry. I am very sorry. It should be VBS. I am sorry. Made a mistake. That is why I think you might have got worried. VSB or VSB. Okay. I am sorry. Okay. What is this GMB VSB? This is another current source. What is the, okay, this is plus value. So what, whether it will add to the net current or it will subtract? Both are in no same sense. They will add. दोनों एक ही डायरेक्शन में है. So GM VGS plus GMB VSB total current इतना है वहाँ पर. इसका हाँ वो कैपिटल VSB है. Actually biased के कारण अभी आपको इसका quickly example देते हैं why we are saying so. Just now few minutes ago I said we assume Vt is constant. What did I say? Vt is constant. But in real life, Vt is also decided by how much is the bulk voltage. Just now few minutes ago I said if I apply minus VSB to the bulk, what happens to say source drain and gate source bulk and drain bulk? The depletion layer enhances. Is that correct? If you know your theory well, MOS transistor theory, any depletion charge below the channel, where does it contributes to in Vt? Minus QB by Cox. You add an additional QB, the Vt will enhance. The expression given is Vt is equal to Vt0, that is 0 VSB value, plus gamma times, gamma is a constant under root 2 phi, some value I will explain, 2 phi f Fermi level, Fermi voltage, plus VSB minus 2 phi f to the power half. So essentially saying with VSB it is Vt, without VSB it is Vt0. So additional Vt will appear if negative bias, is that point clear? If there is a depletion layer in the channel region now because of the source drain, then the additional charge in the depletion layer enhances the Vt value, because there the value was QB by Cox. Initial depletion was because of what? Because of the gate voltage I am applying. Now there is additional bias I am giving from bottom plate. It will also put large depletion charge at the channel side. That additional charge will enhance Vt. By same logic, if I were to put VSB positive, what would have happened? Vt would have gone down. This is fantastic. This in 4th year or some year later, if you are engineers in this area, VLSI, anytime, or in communication chip designs, then you will realize that Vt control is now external. Source terminal बाहर है, अंदर तो फिक्स है सब ट्रांजिस्टर के, बट पीछे से ही मैं वायर्स लगा के I can vary the Vt of my choice. Okay, this is very great control. This is VSB control. Okay, but that is not my job. If I write this Vt like this, IDS will be like this. If I take delta IDS by delta VSB, which I am defining as GMB, why it is called B? Bulk. Okay, transconductance, change in current with change in bulk voltage is called GMB. Okay, bulk transconductance. That is can be, if I differentiate this, I get gamma upon 2 phi f plus VSB times GM, and this whole factor gamma upon 2 phi f plus under root of this is given a name eta. Is given a name eta. Okay, typical eta value is 0.6. So how much is an equivalent circuit? Let's say GM VGS is some value and GMB is how much? 0.6 GM value है वहाँ पर, तो actually 1.6 GM मिलेगा आपको यदि VSB लगाया तो, अदरवाइज सिर्फ 1 GM मिल रहा था, अभी 1.6 GM value आपको हम दे सकते हैं. Is that clear to you? That's the trick in actually controlling the gains. Substrate bias can actually change the gain. So is that GM, in our cases sometimes we may say GMB 0 you need not use, but just because that actual circuit equivalent was shown, GMB value may be specified and maybe you draw it there. Okay, is that okay? Okay, okay. I have a MOS transistor. Right now I am not showing you any great DC things here, no biasing, that's what we will start next time. I am actually biasing this circuit by something what is called constant current source. Okay, what is the impedance of constant current source? Infinite. That's why it's called constant current source. So output resistance of a constant current source is infinite. Is that clear? So I am biasing with a DC bias current IDS, capital IDS. So DC current is pushed through this. I am putting a V in, I am finding V0 here and an amplifier. I want to find V0 by V in, the gain. If you have done network theory and Professor Narayan being so great, one can say change in this at this 2-port network, if I solve here, change in current through this transistor if delta IDS, it can be written as Gm times Vin plus G0 times V0. This is network, 2 port equivalent network, G0 Gm shunting, Gm VGS R0. R0 is 1 upon R0 is G0. So I say Gm Vin, ये लिखा है ना, फिगर दिखा है आपको यहाँ पर, हाँ, Gm Vin plus G0 V0 is delta IDS. Change in current through the transistor if I apply Vn. Okay. Now current source biasing, since we did, we define Gm. Now that is the definition of small signal values. Gm is delta IDS by Vn. In what condition? When V0 is, when this term 0, then delta IDS by Vn is Gm. By same logic, G0 is equal to delta IDS by V0 when Vn is 0. Maths, nothing great. एक टर्म को 0 करो तो दूसरा मिलता है, इस टर्म को 0 करो तो ये मिलता है. Simple maths. However, please look at the situation. IDS is a fixed current. Okay, DC fixed current. Okay, so delta IDS there is no change because that's what I say, fixed DC current. If delta IDS is 0 and I substitute here, then Gm Vn plus G0 V0 is 0. So V0 by Vn is Gm by G0 minus और माइनस Gm R0. वो जो पहले आपको निकाल के दिया था ना एक्सप्रेशन, वो देखो इससे भी आता है, 2 पोर्ट नेटवर्क से भी आता है. So depends on how do you want to solve a circuit, the result would be same from any way. Is that correct? What is V0 by Vn means? The gain, AV, voltage gain. So voltage gain of a transistor is when biased with constant current source is, that's why I call intrinsic, Gm times R0. Next time we'll start the actual MOSFET amplifiers. First we'll start with biasing, then we'll show you some amplifiers, and then we'll do bipolar. Why we want to postpone bipolar? Because as I said 60-70% MOS hai, so let's do MOS first. Thank you for the day.